I'm Daniel Finkel. I'm Senior AI Engineer at Thingworx Analytics. I am not Alex Kipman. I'm sorry. I've been confused with him quite often today so far. And today I'm going to be talking about predictive maintenance with Thingworx 101. So first off, what is predictive maintenance? Now, Jim Heppelman touched on this as part of his keynote, but in general, the manufacturing industry has been kind of evolving. It's gone from a reactive maintenance to a preventative maintenance to predictive maintenance approach. With reactive, you wait for something to critically fail, and now you have to quickly rush out and fix it. You're losing time, your assembly line is down, and costs tons of money to fix that. With preventative maintenance, you don't really know when your device is going to fail. You're just trying to play it really safe by saying every month or so we're going to go out and check on the device. And it's going to take time and money to go check on these things. And it might not always be worth it. It might be that this device is not going to fail for another year, and all that time and money was kind of wasted. So the best solution would be predictive maintenance, in that you're actually pulling data from your devices, from your processes, and it is telling you when it thinks it is going to fail. What it's noticing are critical defects that might cause some kind of critical condition in the future. So in general, predictive maintenance is poised to save tons of money and time for all industry. So the big question is, how do you go about creating a predictive maintenance solution? So last year, me and my team, the AI team at Thingworx Analytics, we were here on the show floor, and we actually got to talk to all of you. And we heard all your concerns. How do you actually build a predictive maintenance solution? And so we came back and we thought, hey, let's try and build one. We're developers, but we've never actually built the full end-to-end solution. So let's do that. And how? With Thingworx. So first we sat down and we thought, okay, what are the actual steps? What are we going to need to do? We don't have a $100,000 pump sitting in our office that we can just go up to. We need to first come up with some kind of device that we're going to use to show predictive maintenance in action. And then we're going to have to censor it up so that we can actually collect the data from it, because predictive maintenance requires data. And then from that data, we build a machine learning model. And that's where the analytics part comes in. And that's what's going to do the predictive maintenance for you. Once we have that model, just having it by itself doesn't help you. You need to actually put it out somewhere. You need to be able to access it. You need to be able to get results from it in real time. And then finally, you need to be able to visualize these results in some manner. If these predictions are happening, but they're kind of off going into some kind of server or database somewhere and nobody sees it, you're not getting anything from it. So you need to have some way of visualizing this. So we set out to build this predictive modeling solution. So the device that we ended up choosing was a light bulb. Fairly simple. Again, we don't have a $100,000 pump. Our budget wasn't the greatest. Light bulbs are great. You can get them really small. You can get them in large amounts. If they fail, they're really easy to fix. And the failure itself is very easy to identify when the light no longer burns, when the filament has broken. And the other great aspect of it is we need to collect lots of data. If we have a light bulb running at normal, nominal conditions, it's probably not going to fail on its own for thousands of hours. And we can't just sit there for thousands of hours waiting for these things to fail. So if the light bulb is rated for a certain voltage, we can increase that voltage. And we would expect the time to live to decrease, to drop sharply. And we can increase it higher and higher and higher. There's obviously a limit at which point it'll just break right away, so we can't go above that. So we decided to use a light bulb. And then what we're going to predict the remaining useful life. But just that by itself, there's many ways of interpreting the remaining useful life of the light bulb. You have to look at how precise you're trying to get. Are you trying to say it's going to fail in 10.5 seconds? Or are you going to say it's going to fail within the next 2 years? You want to find this kind of balance. There's the other approach of just using a relative health measurement, having some kind of categorical qualitative description of the relative health of this device. Green, it's healthy. Red, it's probably something's going to go wrong. So could we maybe find something in the middle? And ultimately, what we wanted, what our final product would be, is a device where you could you can have a set of light bulbs. Some of them have been running for hours beforehand, some of them are fresh. You don't know just by looking at the light bulb how much time is left in its life. Normally, you'll look at you can look at the specifications of the light bulb and say, oh, at 1.5 volts, this is rated to live for 10,000 hours. But you don't actually know if this bulb has already been running for 5,000 hours before this. So we want to build a model that can make this distinction. It doesn't need to know how long the light bulb has been running before this. It can just infer that from the information of the light bulb. So we had to make a setup. This is what we did. We're very proud of it. It's very nice. And unfortunately, I could not bring this today because I'm pretty sure I would not have gotten this through airport security. But in the center, you can see there's a little light bulb, and it's enclosed with this plastic casing just to keep out any external variables. We have it connected with a Raspberry Pi that's on the bottom left, and that's what we're going to use to actually collect the data and send it off to wherever it needs to go. And on the right, we've got the power supply, which is going to be actually driving the voltage across the light bulb, and that's what we're going to be modifying. So we had to sensor it up. We use quite a few. We use current and voltage, just general electrical properties that anyone should have in the manufacturing space. You're going to have this kind of information. The current and voltage sensor that's just connected to the Pi and it's just going across the light bulb. We have 2 temperature sensors. One just looking straight at the light bulb from very close up, and that's right there in the center. And we have an ambient temperature sensor just because it might be that this light bulb is running in like a refrigerator for some reason, or in some kind of in the desert. We don't know. It doesn't hurt to have that sensor. We might get some interesting data from it. And we had a light sensor just to measure the illuminance. As you're sending more current through the light bulb, it's going to burn brighter. And maybe we can get some information from the change in illuminance maybe as this light bulb gets closer and closer to failure. And we chose to collect this at 2 hertz just because we thought 2 hertz, 2 measurements every second, that should be enough for us to be able to take action. We don't need 100 measurements per second. It's a small light bulb. We don't care that much. So we started collecting data from it, and this is what we got. This is the lifetime of one light bulb from start to finish. We can see that in the bottom graph is just the voltage and current, and it operates the way you would expect. Voltage in general is going to increase and the current is going to decrease because the resistance is slightly increasing as the filament itself heats up. And you can also see that in the resistance plot in the center. It's increasing, 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 and then all of a sudden some fractures are going to start happening and it's going to break down a little bit. And what's interesting is we can also see the temperature and how that changes, and the illuminance. The temperature kind of stays the same, the ambient temperature especially, because it doesn't care about the light bulb. But the bulb temperature starts to decrease slightly, and the illuminance also has a sharp decrease. And so we are hoping that with this data, we would be able to produce a model that could kind of infer when something is going to fail based off of the physical properties of the light bulb. So now let's get into the machine learning. As I mentioned before, we wanted to measure all the data at 2 hertz. The issue is not all of the sensors that we're working with are going to operate at 2 hertz. Some of them operate at 4, 3 hertz. Others, they take a measurement whenever some kind of physical activity happens, some kind of action takes place, or there's a significant change, and then it'll log that. So we needed to find a way to unify all of that data into a single sampling rate, because that's ultimately what's going to help the model learn better. And so this, fortunately, can just be done with simple scripts on the Raspberry Pi. Again, all the data is going from the sensors to the Raspberry Pi. In there, that's kind of our world. We can do whatever we want in that Raspberry Pi. Little scripts are very easy to write, and they can do many things. After this, we need to actually get this ready for machine learning. So in this plot, we have the time steps going, and then S0, S1, and S2 are just the sensor stream values as they're coming in. And so the red highlighted portion at the bottom represents when the light bulb failed. So it was running and running and running, and you were collecting sensor data, and then ultimately it failed right there. Well, how do you label that failure? A simple way is just to say the time to failure. From the start, it was 3 seconds at the beginning, and then it was 0 seconds at the point of failure. It's a very simple way of describing this problem, and it can be useful for machine learning. However, if you were to build a model in this fashion, your model would be giving you back predictions saying, hey, your light bulb is going to fail in 37 minutes, 62 seconds, and a half. And that might be a little bit too fine-grained of a prediction than what you want. Another solution would be to use the probability of failure within a certain time frame. So in this case, this is probability of failure within the next 2 seconds. By doing it in this method, you're simplifying the problem significantly for the model. Now it's just a Boolean classification. Is it going to fail in some timestamp or time range or not? And again, this could work for our light bulb. We could say, is it going to fail in the next 10 seconds? But maybe 10 seconds isn't enough time to take action. So do we do failure within the next hour? Well, an hour, you're not going to know when you really need to take action on it. So what if we did some kind of ordinal approach, some kind of way of kind of combining the two, discretizing the separate categories of failure? So in this case, you have an order where when it's closer to failure, it will fail in less than 1 second. Then the 3 in the middle are failure within 1 to 2 seconds. And then above that, failure greater than 2 seconds. And this can obviously extrapolate to really any kind of manufacturing problem. It really just depends on what kind of problem you're trying to solve. What information could you use to be able to take better action? So in our case, we're going to choose to use the time to failure, let's say. And we're going to try and build a model with that. So model creation, this is where we get into the actual, how does Thingworx fit into this? Now we have the data. What do we do with it? And this is the model creation part is where analytics server comes in. This is our way of building all of the predictive models for whatever kind of problem that you have. It has been built to be very generalizable, but we've also been putting in lots of effort specifically for the factory use cases. So I want to ask a general question. Has anyone ever built a machine learning solution or predictive maintenance? Has anyone ever gotten right on the first try? The few people I saw with the raised hand said no. It doesn't happen. It is very unlikely to build the best model on your first try. Machine learning, data science in general, it's an iterative process. You're never going to know exactly what's right at the start. That's why you're collecting all this data. And sometimes you might think you know what's right. And then the machine learning model will say, well, no, we actually found this other thing which might function a little bit better. And then you kind of change your perception on how you're reviewing the problem from the start. And so Thingworx Analytics kind of simplifies the model building process, allowing you to fail fast and iterate faster. We take a lot of the busy work, so to speak, out of machine learning out of your hands. We do all the feature selection on our own and the model validation on our own, but we allow you to put in some advanced configurations if you really do want to get in there and tweak it some more. So I'm going to go through some still images of what the platform looks like, what the different aspects of Thingworx looks like, and talk about in general how they are used. So in this case, this is what Builder looks like inside of Thingworx Analytics Server. This is one of the ways that you can go about training a model. And so in the middle, the large section at the bottom, those are the learning parameters. So you can choose decision trees, linear regressions, neural networks, logistic regressions, SVMs. We provide a range of different learning techniques that you can use, because certain techniques are better for some problems rather than others. And we allow you to kind of dig a little bit deeper if you really want to, really change how many layers or nodes are in the neural net, how many trees you're going to use in your gradient boosted models. And on the right, at the top right, we have our time series functionality. So in general, when you're doing predictive maintenance, you care about the temporal component of your data. You care about the time to failure right now, as well as the time to failure 10 hours from now, taking into account everything that has happened in between. So this is a time series problem, and we give you a simple approach to building a time series model. In this case, you put in the kind of look back that you want your model to use. How far back is it going to look in the past in order to build predictions for the future? And when you do build a model, we return to you the validation metrics. So in this case, this was the time to failure model. This is a continuous value. And so we're going to return to you accuracy metrics related to continuous goals that you're trying to predict on. So in this case, we have RMSE, Pearson correlation, and the R squared. Ideally, you want RMSE to be as close to 0. Pearson correlation, you want to be as close to 1. R squared, also closer to 1 is better. And then we have a diagram here. And in this case, this is a diagram showing you, in general, how the predictions were compared to the actual values. So in the dark blue, that means it's more or less like right on point. This is accurate. So ideally, you want the dark blue to go all the way across in like a perfect diagonal. And then you can see here there's a lot of light blues. So in these cases, we're under-predicting. We're predicting it's going to fail quicker than it actually is. And so we can look at these metrics and say, you know, this time to failure model, it seems to be pretty good, but maybe we can build something better. Maybe we can kind of tweak our model parameters, either the learning techniques themselves, or even go back and try a different goal, try to predict on either the probability of failure within some time frame or some kind of ordinal discretization. And so that's what we ended up doing. We found time to failure was pretty good, but not that great. We could do better. And we did that with a categorical ordinal approach to it, where we split it off. We said, if it's going to fail in more than an hour, that's more or less healthy. I don't need to know that it's going to fail in a day or it's going to fail in 2 days. With this little light bulb, if I know it's good for an hour, I'm fine, I can walk away. But then as we can kind of granularize it more and more to the point where as we get closer and closer to failure, we get more specific predictions, more finer predictions. And at the end, if it's less than 15 seconds, that's when you know something is really bad, something is going to break right now. You better jump in and fix this. So this model ended up returning a Pearson correlation of 0.87, again, very high. The accuracy is just the general accuracy. How often, because now it's predicting specific categories, how often was it right on the money? And 69% might not seem that good, but you have to remember there are 8 categories that it's choosing from. If you were to do a random chance, that would be a 12.5% accuracy. So we're doing, I don't know, 4 or 5 times better than just random chance. And if you look at the RMSE, in this regard, because the RMSE is less than 1, what this is saying is, on average, when this model will make a prediction, it will be less than 1 category away from the actual. So if it's saying 1 to 2 minutes and it's wrong, then you can be pretty certain that it's within the bounds of 30 to 60 seconds or 2 to 5 minutes. So you're going to be in the right ballpark anyway. So now that we have this model, we need to operationalize it. And so this is where we get into Thingworx Foundation. Thingworx Foundation lets us build a thing to represent our physical device, kind of like the digital twin. So in here, we can set the different properties of this light bulb. We have ambient temperature, bulb temperature, we have illuminance and current. And this is all going to tie into what's happening in the physical world. But this is all in Thingworx. How do we get the data up from our Raspberry Pi, where all the data is currently being collected, to Thingworx? And that's done through the Java Edge SDK. So in this case, this is real code, by the way. I'm not going to go into the specifics, but this was done. And we're pretty happy with it. So the light bulb thing, so the Java Edge SDK is made up of 2 parts. There's going to be the actual thing, which is going to represent the kind of skeleton structure, the one-to-one twin of what's going to be in Thingworx. And then the Thing client is going to be kind of the brains of this. Thing client is going to determine what you're actually creating the skeleton from, what data you're passing into the skeleton, the thing itself, or you can send it up to Thingworx itself. And so the client is what's in charge of binding the thing from the Edge SDK and sending it up to the thing in Thingworx. So that does all the orchestration of sending data from your physical device up to Thingworx. And then once you have your thing with all of the data being passed into it, all the different sensor values, now how do you configure that to actually make predictions? How do you make it do anything? And this is what Thingworx excels at. Thingworx is made to orchestrate everything in your solution. So you can create a subscription, which will basically say, and you can set it to do more or less what you want. In our case, we set it so that whenever a new value gets populated, a new set of data gets sent in, we are going to send off a request to use our model and make a prediction from it. So as data is streaming in, we send it off and make a prediction with it and then collect it back. And so this is all done through the subscriptions. Again, you can tailor this to do more or less what you want. And this is JavaScript. It's pretty simple to use. So once you have all of this kind of operationalized, we're getting data from the Raspberry Pi, sending it up to Thingworx, and then from Thingworx, we are making a prediction from it. Now we need to visualize this. And so to visualize it, Thingworx has Thingworx Mashups. And with Mashups, you're able to build more or less whatever kind of UI you want. The previous screens that I showed you of the training process and the validation process and all the different configurations and parameters you can have, and that graph, that was all built with Mashups. So you can kind of do what you want with it. You have lots of flexibility in terms of how you want to present this in your factory. And so in our case, we built a little mashup, and this shows as the voltage is increasing. So in this case, it gets brought up to 2.3 volts. We can see that the current in real time was updated, and the illuminance was updated as well. And we also made it so the little light bulb icon kind of starts glowing brighter and brighter. And at the top, we can see the time to failure. Right now, it's 30 to 60 minutes. So temperature is sitting there. Ambient temperature, we noticed, wasn't really changing, but we included it just because. So soon, we'll be increasing the voltage a little bit higher. So in this case, the voltage there, it dropped to, I missed it. We increased the voltage, and the prediction actually dropped to 1 to 2 minutes, because now we were getting closer. We were going higher above the rated voltage. And then we brought it down in time before it failed, and it went back to more than 1 hour. So this is really cool. You can set this up on your computer. You can monitor all kinds of different devices, but we can't really do this presentation without also including AR. So we were able to use Vuforia, specifically Vuforia Studio and Vuforia View, in order to build an AR representation of our light bulb model. So we also included this little gauge, which again, it allows you to see what the actual physical properties of the light bulb are as it's running. You'll notice that the voltage is 1.8, even though the DC power supply is returning 2.2. This is because we have a resistor in series with the light bulb, so that's going to drop the voltage that is being measured across the light bulb. So this is all expected. The current is close enough to what the DC power supply is showing, and we can see what the bulb temperature is. So this was all, we built the AR experience in Vuforia Studio. We published it in the experience server, and then through the Vuforia View, we were able to look at it on our phone or tablet devices. So in this case, so the way we collected data, again, with light bulbs, we're able to collect lots of data very quickly if we increase the voltage rating. So we would run it at 2 volts, and it would fail in maybe 2 hours. We would run it at 2.5 volts, and it would fail in 1 hour. And on and on and on. And we collected 50 different light bulbs worth of data, and we built this model. And so because we used this range of light bulb, or of voltages, our final model is able to generalize well enough. So it doesn't need to see that the voltage being applied is 2.5 or 3 exactly. It can take action even when the voltage is not exactly at those points. In this case, we increased the voltage now to 3.5 volts. And so you'll notice that the prediction itself takes 8 seconds in order to change, and this is because we're using 8 seconds worth of data to make our predictions. So there's a little bit of time